going? Is it happening? I'm live. All right, I did a setting today that lowers the latency. So we might have much less of a delay today. That's what I'm hoping. So I can get to your questions quickly. So, yeah. I'm going to swap it to Chrome and see how long the delay is. Boop! And a 1, and a 2, and a 3, 4. Oh, it's only like a 5-second delay. That is livable, guys. That is livable. Alright. We're going to dial myself up. I'm going to watch my video on my phone. Oh, wow. There's a really low delay. Awesome. Okay. This changes everything. Haha. Okay. I'm very excited. I didn't realize there was that setting at the bottom for stream latency. Patrick is just going to say recursion all day. Oh, come on. Don't. Okay. All right. We're going to do recursion. Today, I'm wearing today's t-shirt. It's brought to you by Word Nerdery. It is a quick brown fox jumping over the lazy brown dog. It is called an omnigram because it uses all of the letters of the English alphabet. And these were popular. Actually, while I'm getting the slides set up, why do you think these were useful in the past? In the days of yore, why did people come up with omnigrams? The reason is interesting. Is that new merch? No, this is an old shirt. It's not new merch. It's an old shirt, but it's new to you guys. So that's exciting. So yeah, why were omnigrams useful? They're not as useful anymore. Well, they're still kind of useful today, actually. Cryptography? No. Graphy is in the answer. 201 merch. I survived. I survived 201. Project 1. I completed the Retriever Trail. That picture is so trippy. Yeah, usually when I put this up in front of students, they go, ugh. Geography. Useful for fonts. Agatha gets it. Oh, and Charlie's right here. Agatha, because she got the right answer, gets a special visit from my little guy. Here he is. Oh, look at this fella. Yeah, it was useful for typography. So if you're looking at different fonts, omnigrams are nice because it will show you all of the characters like in a sentence instead of just the alphabet. They actually would use omnigrams when they would make and sell typewriters. So they would type out the omnigram to make sure all of the typing heads were still working on the typewriter. It's a fun fact about omnigrams and the old days of typewriters because you would have individual key press failures. Man, he is just done with me. He's couch bound. Anyway, so yeah, we're gonna go deeper. We're gonna do more recursion today. There's gonna be a little switcheroo with the schedule, I believe. We're going to do homework 6 before homework or project 2. So your last homework will be coming down the pipe soon, and then project 2, and then project 3, and then we're gonna get the final going. That's his boss title, Charlie the Mutable. I would pay for I Survived 201 shirt. Yeah. Graffiti. I like graffiti. Okay. Alright. So, praise Professor Hamilton. Praise Eric in all of his wisdom and his beneficence and his benevolence and all of his instances. He granted an extension to tonight for Project 1. So you have 24 extra hours. Go, go, go. Hopefully this will let you guys tidy up. Make sure you got all of your bugs removed and tested and you can get those final things polished. So yeah. So praise Professor Hamilton. I was the villain. I was like, no, don't give them an extension. Or was I? Who knows? Who's not done with it? Nobody has to fess up. But keep on keeping on. Yeah, so let's present this. So we're going to talk about some more recursion. So here's the process for solving recursion. I actually use this slide with 341 students that come to my office hours when they're having trouble with recursion. So it doesn't, this is sort of a living document that I keep editing as I give help to people with recursion. This is really tricky. And the thing I always say about recursion is I think it uses a part of your brain that when you're using that part of your brain, the rest of your brain stops working. It's weird. I'll have students in my office hours, and they'll be working on a recursion thing, and I'll be like, okay, and they're thinking through it, and I'll be like, hey, I'll look at a line of their code, and I'll be like, how do you increment a variable? And they'll just like, they'll look at their code, and they'll look at me, and they'll look back at their code, and they'll look at me again, and I'll go, and they'll say, and I'll go, okay, and I make them close their laptop, and I say, how do you increment a variable? Stop thinking about recursion, and they'll go, oh, like variable plus equals 1. Excellent. And then we'll reopen their code, show them their recursive function again, and it'll be like, all right, on this line, how do you increment this variable? And we'll just go, I don't know. And these are really smart people. I think it's just, it's like the tap your head, rub your belly type thing, where it's like, if you're thinking about recursion, everything else, every other thought just kind of gets flushed out of your brain. So if when you're working on homework 6, which is going to have some recursion in it, and you feel like it really makes everybody feel dumb when they're learning how to do something, it's just not a normal thing for our brains to do. So, the one time I don't procrastinate, the due date is extended. Well, you get to sit back and relax. Congratulations, those of you who didn't procrastinate. I'm proud of you. You get to sit back and relax and be like, I don't have anything to do tonight. So that's awesome. Anyway, back to the subject at hand, the process for solving recursion. What is the base case? So the first thing when you're given a problem to solve recursively, we'll use factorial as an example because we went over it last time. The first thing you think about is, what's the easiest problem? What does the final clone do? What is the easiest version of this problem that if I'm given that problem I can go, that's easy to solve. And so that'll be my base case. And so you write an if statement that says, if number equals 1, return 1. If list is empty, do nothing, or return an empty list, or whatever, right? Some real simple version of your problem that you're going to just return the whole answer to. So that's the first thing you do is your base case. And you make sure, you have to think about all of them. There might be more than one. There can be multiple base cases, as we'll see later today. How do I describe a subproblem of my problem? So if I'm given a problem that isn't the base case version, how do I shave a little bit off? How do I like get one of those fancy mandolins that they use to shave? It's not like a jing mandolin. It's like got a little blade in it. How do I shave just a little bit of the problem off and then have a slightly smaller problem that I can go ask somebody else to deal with? Okay? And so what I have to know is that when I'm shaving a little bit of this problem off over and over, like when you go to the deli and they got that, you have to eventually get to one of your base cases. So if you miss a base case, or if you're not like shaving down to your base case, failures on 1 and 2 are how you get infinite recursions, where it'll say recursion depth exceeded, blah, 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 blah. It's because you didn't think of a base case, like you missed one, or you're not shaving the problem down to a base case. How many people tried to tap their head and rub their belly? I'm actually weirdly good at it. I don't know whether it's because I'm left-handed or just maybe I don't know. I don't know why I don't have trouble with it. Maybe all the years of like playing guitar or whatever. Okay. Okay. So if I'm convinced that I'm cutting my problem down and that cutting the problem down many, 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 many times will always make me reach a base case, This is where I have to start trusting my recursive call. I have to trust it. I have to trust that it's doing its job. And there's a lot of you, like if you're writing, especially in this class, solutions to recursive problems that are like long, like 30 lines, that usually is an indicator to me. Like if you brought your code for a recursive problem up to me and I saw like 30 or 40 lines, that means that you haven't trusted your recursive call. Because your recursive call is a function, you have to think of it, it's your clone, right? They're solving the same problem you are. So they're taking the same kind of input and they're giving you the same kind of output in return. And so you have to trust that it's going to do its job correctly. It's actually really hard to do. It's a real, like, faithful thing. Oh, okay, yeah. So Emma says, this is just like induction. It is just like induction. Emma is correct. But that's like, for a lot of people here, explaining a thing with a more complicated thing. So, well, not complicated, but esoteric, perhaps. But if you're a math person and you get induction, the process about thinking about recursion is very, very similar. It's about taking a problem at a specific point and shaving it down so that it can get back to its base case. Then, what you have to do is, I've shaved a little bit of the problem off, so I have my little bit of the problem that I'm going to solve, and then I have the solution that I trust my recursive call gave me, right? So with factorial, I shave the problem down by subtracting 1 from the number I'm giving factorial for. So if I was asked for factorial of 582, I'm going to ask my clone to compute the factorial of 581. Which means I have 582 still, and then I have 581 factorial is what's coming back from my clone. And I have to figure out, well, how do I take the solution to that smaller problem and combine the solution to my little problem to get the solution that I'm going to go hand back, right? So this is a big thing. There's a reason this is in large letters with italics and underlined and bold, and it's just... is that so many people, they get the base case, they get the recursive call correct, and they don't do anything with it. And the way you'll know that this is happening is if you keep getting your base cases solution back for everything, okay? So I'm trying to help you guys with this process. Each one of these steps, if you don't do them correctly, has some symptom that manifests in your code, right? So if 1 and 2 fail, you get an infinite recursion. A failure at 2b means your code's really long and complicated. It probably doesn't need to be, and you've probably introduced errors in the complexity that you've added. And then number 3, if you don't do something with what your clone gives you, nobody's doing anything with what their clone's giving them, which means that everybody's just passing along that one page on narwhals, just all the way, right? And so you have to do your part in each exercise. And I should be careful that I'm returning the answer to my problem, not the answer to the recursive calls problem or something else. Like you have to be, when you're working on recursion, you have to be crystal clear about what it is your recursion is supposed to be doing and what your function you're writing is supposed to be doing, and what you get back from your recursion is the same thing as that. So you have to be really crystal and clear on that. All right. What do we got here? There is only induction and deduction. There's abduction, right? 203 teaches both. I like reduction. Abduction's a statistics thing. Alright. I don't see anything in the chat. As a math major, recursion definitely makes more sense for me than it usually does for my comp sci friends. Yeah. I will say that recursion is... this was the way Dr. Gibson described it to me. It's something, and I agree with her wholeheartedly, it's something that you're going to have like a light turn on. A lot of people, you just kind of, you have to practice a bunch of problems, and then eventually it's kind of like something clicks or twists rotates into the right place in your brain. And then it's like, oh, that's how it works. So that's why I try to pummel you guys with a whole bunch of different analogies and exercises and things like that, because different things click for different people. And I've heard from a bunch of different students, they'll be like, oh, when you said this, it did that. And so it's at some point you're going to have your breakthrough. Usually you have some amount of understanding in 201, and then when you get to 341 and you're doing trees and all this other stuff, then you're like, oh, I really get it now, because there's almost like a physical representation of the recursion you're doing. There's a whole big LA conversation. I like it. Yeah, Agatha agrees. It's good to hear. Trees are fantastic. So, yeah, anyway, all right. So this slide, like, copy this slide, print it out, put it above your computer when you're working on homework 6. This slide is darn important, because it'll really help you, especially if you're really, really stuck. Just sit back and look at it, because it'll give you a set of reminders of things that you might not have done correctly. A lot of times the best way to solve your programming problems are to not look at your code and think about what you're trying to do, and then your brain will start to think, oh, did I try this? Did I try that? Am I doing this or that? I don't remember if I did that. And so then you come back to your code with a bit more fresh eyes, and you can go right to the problem. So like I always tell people, this is what I did in school. Your mileage may vary, but I would take a shower when I was stuck. And I tell this story, although I probably already told it 4 times in this class, but I'm going to tell it again because it's worth telling. I had an AI project where I had to do an automatic theorem prover, and I took 8 showers in one day. My roommates thought I was absolutely out of my mind, but I was very clean, and I had a functional theorem prover. I would eventually get into the shower and be like, oh, I didn't check for that, and just turn everything off and go back. And so for me, that was the sort of getting away from it and thinking. Since then, I've learned I can go take walks or cook or clean, which are much more productive than taking 8 showers in a day, to get away from my code and think more objectively about it. Prolog gang. Oh, yes. I have actually done industrial Prolog. I have professionally programmed in Prolog for Watson. It was amazing. I had a dream about recursion. I'm sorry to hear that. What's some good practice problems to do? Go on the internet and look up recursion practice problems, and there's a wealth of them. And just find the ones that, some of them have them rated by difficulty. I would try to find that, because some places they'll just list a whole bunch of them, and it'll be like, I'll go down them and be like, easy, easy, whoa, hard. But it's kind of hard to tell as somebody who hasn't solved the problem before how hard it's going to be. So if you can find them grouped in easy and hard. Practice is coming down the pipe with homework 6, though. Rip your water bill. I was in campus housing. No water bill for me. If you dream about recursion, do you really ever stop? If you have a dream about recursion wherein you go to sleep and dream about recursion, then you're doing it right. All right, so let's talk about stacks. I need props. I forgot I was doing this today. All right. Un moment. Yeah? Jules? Jules, do you want to be in my stack? You do. Alright. Here we go. Let's see. What's the delay? Yeah, it's about 5-6 seconds. Stack the pets! They are pretty stackable. They will snuggle up fairly often. Alright, let me go to OBS. Alright, you can see the glory of my omnigram. Alright, suppose I have this blank table here. And we'll say this is an empty stack. Okay? So, up until now, we've had things like lists. So I could have, the first element of my list is a choo-choo train. And the second element of my list is a Coke can. And the third element of my list is a pen, right? And I can access any of these individually. Actually, we're going to go to full camera mode. Are we? We are. Boom. Haha. Right? So if I want to get the first element of the list... Wait, does this make sense? No. First element of the list, we'll say this is the first element of the list. This would be at index 0. This would be at index 1. And this would be at index 2. Choo-choo. Is this like the stack in Magic the Gathering? Yeah, it is, actually. So if you understand that, you're golden. But for everyone else, back to this. Okay. So it is exactly like the stack in Magic the Gathering. Okay. So this is a list, and I can get any element individually, right? If I want Coke can, I just say list at 1, and I get the Coke can, and I can, hey, take a sip of, flavor. Okay. Or if I want to access the pen, I just say index 0, and I pull up the pen, and I can write with the pen or do whatever I want, right? So I have access to all of these things. But now we're going to talk about a stack. So what we're going to use from a stack is my writing tablet. So I'm going to put something in my stack. So I'm going to push, the term for inserting into a stack is push. So I'm going to push into my stack my first element of data. Okay, so this is now at the top of my stack is a tablet. Now I'm going to push a roll of tape. Okay, now I can't access the tablet, like I can't use the whole tablet until I get rid of this roll of tape, right? Like it's gonna be, this roll of tape is in the way. So I've pushed a second thing on top of the first thing. So now this is the only thing that I can really access or do something with. Like if I want to access the roll of tape, I can immediately remove it in what's called a pop. So it's pushes to go in and pops to come off. So I pop this off, and maybe I peel a bit of tape. Let's see. I peel a bit of tape off and make a fashionable, we'll say, ring for my finger. Wow, incredible fashion. So now I have access to the tablet. But if I wanna blog on the Socimeds about my cool new ring, I have to pop this off to make this the top of my stack so that I can edit it, and then I can push this back on, right? And so I can keep stacking things like flashlight and train and napkin. Oh geez. Oh geez. Right? So now, if I want to access the tablet at the bottom, I have to pop all the things on top. So I have to pop the Cheers napkin, and then I have to pop the train, and then I have to pop the flashlight, and then I have to pop the masking tape and resist the temptation to further accessorize, and then I have my tablet access to me. So the point is, with a list, you can access all of the items at once. With a stack, you can only really access the top item. And if you want to get to lower items, you have to pop the things off the top of the stack so that you can get to the items that are at the bottom. Okay. Yeah, last in, first out. So they're the opposite of a line at the grocery store, where you're first in, first out. Stacks are last in. Stacks are like the worst. Stacks are grocery lines made to enrage people. Wait, they got here just now and you're going to deal with them first? When I'm feeling particularly stressed out and have a short attention span, my office can act like that. Someone will show up and be like, oh, how can I help you, when there's 4 people sitting there, right? But, so stacks are, and I always mess this up, so I always have to think about it. Stacks are first in, first in, first out, and queues are, something just fell off my table. Queues are first in, first out. But we're not going to talk about queues. We'll talk about queues in 202, I think, possibly, and then definitely in data structures. You'll be sick of them. We do a lot of time on queues. Queues, priority queues, sometimes even P's and R's. Just kidding. No other letters. All right, let's go look at some questions. I'm going to look at some questions. I see the lecture assistants are, as usual, being awesome and helping out. Did you just use list as an excuse to drink Coke? It was actually flat. So, instant regrets. Magic the Gathering is Turing complete? Yeah, I guess. Sweet. Alright. Okay, so Richard asked, I thought push puts it at the start of the list and pop takes it from the end. So push, at this point in 201, just think of it conceptually as a stack on a table. Push puts a thing on the top, and pop takes the thing off the top. So if you follow a push with a pop immediately, you'll be getting the same thing that you just pushed on. Don't worry about Turing stuff, my word. If you want to learn about that, you'll take a 400 level class called Automata Theory. It's really interesting. What's the practical use of this? So this is how function calls are managed. And we're going to look at that in a second. We are expected to know about 201 things. Can we see this in live code? You sure can. Here we go. Did the stream freeze? Oh no, it's just me talking. Okay. Python. Uh-oh. Stand by. I know it's dark. Don't freak out. I'm aware. I'm on top of it. Is it still dark? Okay. I'm on top of it. I appreciate when you guys like flip out though, because still because I did lecture to darkness. I'm a real mess when it comes to 341. Okay, there's a thing. That's the bot that manages office hours. Haha. Okay. Wait. Screen is black. Thank you. Okay, so let's go back and look at factorial. So I'm going to debug factorial. Okay. This thing on the left-hand side is a stack, and we're going to watch it get pushed onto the top of it. So we're going to go in here, and so now we have factorial live where number is 7. Okay, so number 7 in this particular version, and this is why we're discussing this in recursion, is as you make recursive calls, like I step into here, another recursive call has been added to the top of the stack. So the top of the stack is 6, and right underneath of it is 7. 6 is the function that we're actively looking at, and 7 is the one that called the one that we're actively looking at. So I can repeat this procedure and step in and step over, step in, and look, the stack on the bottom left is growing. This keeps growing. Okay, so we're down to 3, we're down to 2, and we're down to 1. Okay, so now we're gonna, because we've reached a base case, we're gonna return 1. Now our stack's quite tall, so as we start to return things, once a function is completed, it gets removed from the top of the stack. This is called the call stack. So once a function's call has been completed, it gets popped off of the top of the call stack, and then control resumes in the function that is now the top of the stack. So that'll be, once the factorial call with number equaling 1 has been completed, then it will go back to this call on line 23 that number 2 is waiting for the result from number 1. So let's do that. Boop. And now we're on the top, and we're looking at where number 1 exists. We're looking at where the number is set to 2. So where the base case has been popped off the stack. So now this one's going to return 2 to the other call. So this return 2, and now we're going to multiply that by 3 to get 6. And as we execute that return statement, the stack is going to get things popped off of it. until finally we're back to our original call, where now we have the solution to 6 factorial. We're going to multiply that by 7. And now we're back to the top level function. We'll kick over once and see that the print statement prints out 5040. Wait, you guys can't see anything changing? Damn! What? Oh my gosh. This is ridiculously frustrating. Okay. I wish I could say this was the good night, sweet bot. Why is it still trying to look there? Oh my gosh. Trees. What the heck? It doesn't even see pie chart anymore? What's going on? Please wait. Technical difficulties. That's some 341 stuff. Don't freak out. The bot is Charlie. Alright, let's see if it, like, embiggens correctly. Boom! Alright. I'm gonna go over all that again. Oops. Sorry, guys. Stop and rerun. Step into. Alright. So, on the bottom left here, there is a stack. I'm going to watch the stream. Okay, cool. Yes, on the bottom left, there is a stack. We have called factorial with 7, so it's at the top of the stack. Underneath of it is sort of our main program, where it says just module. That's our main program. So the top of the stack is the most recently called function. We're going to step through it to where the recursive call is. Now, I'm going to step into this, which will execute the recursive function. And now we see that there's 2 things on our stack. So we have this old version here with 7. Dream die? Did it die? Wait for it. Okay, sorry about that. Looked like the stream died, and then I was gonna have it was gonna throw a temper tantrum. So we're gonna step into this. Do it again, and see now each time the number's going down. We're at 3, we're at 2, and we're at 1, right? So there's all these calls with 7, 6, 5, 4, and the number's going down because I'm subtracting 1 from the number on each recursive call. So the stack is like actually right here, and the top of the stack is the most recent call, and then so when a return statement is hit right here, then the thing that's on the top of the stack gets kicked off, and then it goes down to the one below it on the stack. Okay? And so as the functions return from the recursion, the stack gets smaller and smaller as things are popped off until we're back to the main program. This code looks very scary. Any questions? Debugger is hard to use. Yes, it was. I did have to click several buttons. Okay, so that's stacks. So there is a call stack. When you get an error printed out and it prints out all those line numbers, it's printing. That's a print of the call stack, or a dump of the call stack. There's, I think, a function in Java that's like dump stack trace. So they're all referring to stack there. I don't know what is up with my OBS that it does that flicker. Okay. Let's go back to home. Yeah. Let's have another visualization of stacks, because we do it. Tell me about the heap. No. I'll tell you when you're older. Oh, it's 1. Dun dun dun. Can I begin this? Push. 2. Dun dun dun. Push. 5. Dun dun dun. So now if I pop, what's gonna pop off? It's 5. Dun dun dun. Goodbye. And if I push it 2, dun dun dun, it's goodbye. And 1, dun dun dun, it's gone. Homework 6 is out. Woo! Get excited. Yeah. Homework 6 is out. Don't buy 202 merch. It's due Monday. Oh. Yeah, you only get a week for the homeworks. Okay. All right. So that's stacks. Any questions about stacks? I'm pretty tired of saying stacks. It looks not fun. Focus, people. Focus. It's a homework. It'll be fun. Dixon's fantastic. I've had... So there's a student that hangs outside of Professor Dixon's office, and whenever I go in there to chat with him, the student says that it sounds like it's just one person talking to themselves. I don't think we sound that much alike, but anyway. This is a very topical would you rather. So your feet are on the wrong legs. So left foot's on your right leg, right foot's on your left leg. Or you cry when it rains. Yeah. So recursion makes us feel awkward, and it sometimes makes us cry. What's the news on exam 2? It's next week, and it'll be take home. That's the news. I have 2 left feet anyway. Take the cry when it rains easy. I love this. This one actually never goes evenly. It always goes towards cry, and that makes me feel good because I'm glad that so many of you are comfortable expressing yourself. How hard do we cry? Excellent question. You cry with proportion to how hard it's raining. So if it's just a light mist, maybe just a single tear. But if it's coming down like real hard, like hurricane weather, you might ugly cry for 10 minutes. And here's the other thing is you cry every time you again notice that it's raining outside. So for instance, if it starts raining, you might cry a little bit, and then you go into a movie theater and watch a movie. When you come back outside, even if it's been raining the whole time, you're going to realize again that it's raining and cry again. But if you just sit by a window and you notice it's raining and you look away and come back, it won't inspire crying again. Cry even when indoors. Yeah, it's just when you notice that there's rain happening. How long to complete? The most torrential downpour. I love how we need to use torrential to describe other things other than downpours or rain, right? Torrential is such a good word. Torrential, like it's a torrent of something. Like he cussed me out torrentially. Like that's so good. We need to use torrential more collectively. We got to make that on our to-do list. So torrential downpour is like 20 minutes of ugly crying and then you're done. So like giant hurricane, you're ugly crying for 20 minutes and then you recover. An average rain, you'll be like, sorry, when it rains, I get a little... Torrent, see, a torrent of, that's good, but we need to use torrential. The flow of students into office hours on Fridays is torrential. Will hard liquor help with the crying? It never does. Do emotions accompanying the crying? you're not really that sad. It's just sort of a thing that you do. All right, I'm gonna do the straw poll, and this time I'll remember. Any other questions? Everybody's fine with the wrong foot thing. Feet or rain cry. Go on, you can type in feet. Rain cry. We definitely want that IP duplication checking. Definitely want to keep up with the integrity of these. How long are our feet on the wrong legs? Rest of your life. Just like you're gonna cry when it rains for the rest of your life. Though I think that would be kind of an adorable trait in like an older person. Like if you're a 70-year-old man who's just like, I just cry when it rains. Like that's really endearing, right? When I run with a wrong feet thing, do I end up running in circles? No, you're just going to have a real difficult time walking for a while, and there might be certain activities that you just can't quite do very well. How long do we have to complete? Details about the take-home exam are not sorted yet, so stand by. Feet. All right, I'm going to look at the results. I think it's live. Whoa! 19 for the crying and 3 for the feet. Woo! Man. Alright. I would probably take the crying as well, I'm not gonna lie. I'd probably take the crying. Alright. Here we go. Here we go! So the Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, 21, 34. What's the pattern? How do we write a loop for this? Roger Dodger in the 26th and a half century. Is that a Starship Troopers reference? You took the wrong section in this class if you're doing Starship Trooper references. Eric Hamilton loves Starship Troopers. Loves it. Almost as much as like Doom. So what's the pattern first? What is the pattern here? How do I come up with the next term after 34? What is the next term after 34? Wait, is it in the GIF? Crap. But how did I come up with that next term? Yeah, it's the number plus, it's, so 1 plus 1 is 2, let's get my pointer. 1 plus 1 is 2, 1 plus 2 is 3, this is like a sing-along. 2 plus 3 is 5, 5 plus 8 is 13, 8 plus 13 is 21, so each term is the sum of the two terms before it. That's it. So how would we write a function that uses a loop to determine the nth term in the Fibonacci sequence? How would we write a loopy loop? And the answer is annoying. N plus n minus 1? Yeah, or n minus 1 plus n minus 2. N equals n minus 1 plus n minus 2. Okay. And now I'm waiting for Emma to jump in with, these are recurrence relations. We can just, and we can come up with a summation and then show, and then it's like, math. All right, sea lion, here we go. Wait, not sea lion. Woo, woo. That's 341. Woo. All right. Back to the comfortable lands of 201. Woo. Cool. All right. So let's do a new thing. We'll call it fib. We're just gonna say for I in range 10 print fib I, and then we're gonna implement fib. Is this working? It looks like it's working. Excellent. I'm gonna make it big so you guys can see what I'm doing. All right, so we're going to do this with a for loop first. So how do we do it with a for loop? So if number equals 1, return 1. If number equals 2, return 2, or 1. So then previous equals 1. To previous equals 1. Then we're going to say for I in range 3 to number plus 1. Actually, I'm going to change this to nth. Shouldn't that be an elif? Doesn't have to be because there's a return statement. Doesn't have to be. Could be, and it would do the same thing. I kind of deliberately slipped that in there. Thanks for asking the question. Okay. So what goes in here? Well, we'll say temp equals previous plus to previous. Temp equals previous plus to previous. Then to previous equals previous. And previous equals temp. And then I think we just return temp. No, we return previous. Whoops. Previous. I think this works. I think it works. What about 0? For this, we're going to say that the first term of the Fibonacci sequence is 1 and the second term is 1. We're not going to say there's a 0th term here. Good question, though. We've gotten so trained at this point to worry about 0, when sometimes we don't. Sometimes we use counting numbers. Okay, let's run it. Oh, I messed it up. Wait, did I mess it up? Yes. It's 1 off. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. Is it just 3 to nth? So this is why this is so fiddly and weird. No, that was just more 1. Nth minus 1? Oh gosh, it's getting worse. How is it getting worse? Plus 2? Okay, I need to think instead of just messing with this. If it's 3, I'm just going to say temp equals 1. Return temp. We're going to start this at 3. And we're going to go to nth plus 1. No, just nth. That's still wrong. Why? Oh, 0th term. Duh. Adoy. So it was working before. 1th term. Okay. It was working before. I made a boo-boo down here. I should have been going from 1 to 9. Or we can go from 1 to 11. So this code is kind of, I don't like it. It's kind of weird. I guess maybe that's what Talia was asking about. Oops. The 2nd term and the 1st term. So this code's a little weird. It's a little weird. So how do I do this recursively? So we're going to call this fib iter for iteratively. And then we're going to do def fib nth. And then we're going to do it recursively. Return the nth term of the fib sequence. Oh my gosh, that's a big truck. I'll give you guys time to think about it. You can discuss solutions in chat. Chat has seemed to have paused on my phone, and I don't believe that you guys aren't gregarious. No, okay. It's just not going. You guys haven't had the chatty chats. Is it raining where you are? Oh, Sajel just gave us some amount of answer. A strong maybe. All right, let's go back to I'm gonna grab the slide that he'll print out, hang up prominently in your home. All right, let's go through this thought process. What are my base cases? Well, my base cases are pretty much up here, right? So if nth is equal to 1 or 2, I just return 1 or 2. Those are my base cases. So how do I describe a sub-problem of my problem? So I've been asked for the nth term. Well, how did we define the nth term earlier? Well, I said the nth term is equal to the previous term plus the term 2 back. So what if I just do that? Nth minus 1 plus nth minus 2. If I keep doing that, do I get a base case eventually? Well, what if I'm at fib 3? I'll be asking for fib 1 and fib 2. So that's good. And if I'm at fib 4, I'll be asking for fib 2 and fib 3. So that's good. The problem is we wouldn't... Here's what you might be tempted to do, is just have that in there, and this will give you an infinite recursion, because if I ask for fib 2, I'll be asking for fib 1 and fib 0, and then fib 0 will ask for fib -1 and negative. Well, it's just print it out. It's going to go crazy town, though. Print nth. And we'll just do fib. We'll just do fib 10. Maximum recursion depth. Like, see, look, it just went forever because it... Let's go all the way up. It got 10, 9, 8, 7, 6, 5, 4, 3, 2, 0, -1. How'd it get to 0? Well, when it was on the 1 for 2, it called 2 minus 1, which is 1, and 2 minus 2, which is 2, or sorry, 0, and then that one kept calling smaller and smaller values. So we got to have this other base case in here, right? So this is how if you don't think of all the base cases, you're going to get an infinite recursion. How am I describing my subproblem? I'm saying it's the previous two terms. So that's my subproblem. If I repeat making that problem, do I get a base case? Yeah, now that I have two of them. If I only had one, I could actually skip over my base case and get an infinite recursion. At this point, we should trust that the recursive calls are giving us the right thing. I do. And assuming that I have the solution to the subproblem, how do I solve my problem with it? Well, if I have the two subproblem solutions, just add them together and return them. And I should make sure that I'm returning the answer to my problem. So I'm not just returning the n-2 or the n-1 solution. I'm combining them. So I expect this to work. Haha! Oh, wait, I still have that printing in there. I'll just comment this out for a second. 55. It worked. That's it. That's it. So if we look, we have this code that's kind of like this weird, you keep track of the previous two terms, and you iterate through, and it's, I don't know, it's just, this is the thing where we do the Fibonacci is one line of code. All right, now, voting in chat, vote loop for loop is more efficient, or recursive for recursive is more efficient. Which one of these functions is more efficient? Vote in chat. Vote, vote, vote. I want to see. Vote, vote, vote. Loop is more efficient. Recursion is more efficient. Recursive, recursive. Ba-da-da-da-da. People are saying recursive. Recursive, 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 recursive. Dun, 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 dun. I like using the loop better. Talia says loop. Dun, 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 dun. Dun, dun, dun. We do have a known range. We're always going to ask for some term. But which gives more headaches? I mean, you saw how long it took me to get the iterative one working. Recursive requires less variables, but I'm talking about efficiency. So the reason I asked this question, this is not a 201 question. In 201, we do not ask you to write efficient. This is a really bright flashlight. We do not ask you to write efficient code. We just ask you to write code that works for all of the inputs that we can send at it, which is a difficult enough problem. It's when you get to 341 and 441 that we're going to start to add, and maybe a little bit in 202, we're going to start to ask you to actually write efficient code. The answer is the loop is more efficient. Oh, the loop is more efficient. And I'm about to show you why. Okay? So for nth, right, if I look at this, so the question of efficiency is how many lines of code get executed. Not how many kinds of code are written, but how many lines of code are executed. So we've got these lines of code. Say nth is 5,000, right? So I have these lines of code getting executed here. So that's like 6 lines of code, fine. And then if I have 5,000, if nth is 5,000, then this is going to run 4,997 times 3, which is a lot, 12,000 something, right? So 12,000 lines of code. This one's going to run a lot more, like a lot more. So we're going to make, this is a forbidden magic because it's a global variable, but I just want to show you. Wait, what? Oh. This is forbidden magic. Forbidden magic! Do not use global variables! I'm just using it to simplify my life. And then we're going to print So let's run it. Oh, I have to do it with... I said, how many? 5,000? Oh, I hope it finishes. Oh, maximum recursion depth. Okay, let's say 500. There's also that problem. Is it? What? It's just not finishing. All right? Just to clarify, I killed it. I turned it off. I'm going to do fib-iter. Boop. Done. Immediately. Done. That's how much faster it is. So, what I don't want you to take away from 201 is that recursion is the best thing ever and you should make everything recursive and so on and so forth. It's not. However, some problems can be more elegantly coded with recursion, which is nice. And also some problems really can't use iteration, or it's insanely clumsy to use iteration. So, you have to resort to recursion, right? So that's kind of the takeaway. I need to download more RAM. This is what you get for using global veins. Yeah, so it's just super slow. And I'm going to illustrate that for you guys to hopefully give you a sense of how recursion actually works. I think this is the first time I'm using my fancy Photoshop setup. Fancy. All right. Photoshop isn't showing up. At least I caught that. It doesn't like to show up sometimes. Show OBS. Hello times a million. I'm such a child. Okay. Done. Which one of these is Zoom? Oh, it's... Aha, okay. So, here we go. So let's say we're doing fib of 5, all right? So this is the recursive solution. What recursive calls are we going to make? Well, we're going to add together fib of 4, and I'm going to zoom out a little. Whoops. 4. Fib of 4 and fib of fid. Fib of fid again. Fib of 3, right? I'm adding these two together. But fib of 3 is going to call fib of 2 and fib of 1. And fib of 4 is going to call fib of 3 and fib of 2. And fib of 3 is going to call fib of 2 plus fib of 1. Okay, so I go over here. Like, this is a base case. 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 And this is a base case. But look at this. Look at this. Look at this crazy town. The fib 2 has been called 3 times. 3 times. 3 times. So we're doing all that work over and over again. The iterative solution only calculates the second Fibonacci term once. Does it once. This one's doing it 3 times, and that's just for fib of 5. Imagine, if you will, imagine up here, this call of fib of 5 was for fib of 6, which means I have a fib, this is going to add together fib of 4 down here. And fib of 4 is all this stuff over on the left. So it's fib of 3 plus fib of 2 plus fib of 2 plus fib of, fib of 1, right? So then there's another 2. So when I calculate fib of 6, I'm now calculating fib of 2 5 times, and fib of 3 times, and fib of 4 2 times. And so it turns out that you do a lot of extra work when you're doing this recursive solution, right? Once you've calculated the second Fibonacci term, you should probably remember that and not have to redo it. So there's actually an optimization you can do that makes the recursive calls remember or see if somebody else has already solved that subproblem, which will cut down on all of this duplication and make it run basically about as fast as the iterative solution. And this is called dynamic programming, and you won't be bothered with that until 441. Oh, Ryan got it. Yeah, so dynamic programming is already brought up in the chat. But yeah, so this is, again, to drive home the point that recursion is not always faster, and to really, really, really drive home the point with you guys, because I hear this all the time from 201 students, is I don't think my answer is very efficient. And I'll say, well, why do you think that is? And they'll be like, well, look how many lines of code there are. There could be, we saw that like the iterative solution is like twice as much code, but it is in fact inconceivably faster. Like for 500, it didn't even finish. I had to turn it off because we were tired of waiting, and it was instantaneous for the longer lines of code. So you'll get an appreciation for this later, but don't worry about efficiency in 201. Worry about correctness. Dynamic programming is cool. I actually really like dynamic programming. When I learned it, I thought it was a nightmare. But now I think it's really cool. You know, sometimes we come around on things. Oh! Jules, is there a bird? Oh my gosh, Jules found a bird. Jules! Well, he's like huffing and puffing. Alright, cool. So we're back. Alright, it's 2:38 or 12. It's 12:38, so we got 7 minutes. Oh, there's doggies. So all of these problems, you'll notice there's things that you can solve, like even just with operators and things like that. Again, this is just to give you practice with the concept of recursion and using it. A lot of people get like real excited about recursion and try to use it everywhere. And as I've hopefully just shown you, it's not ideal. Having more than 4 if statements is bad, or so the internet says. Alright, I'm going to show you one more hilarious bit of code. Are you guys ready for hilarious code? It's going to be funny. Oh my gosh. Get ready to laugh at this hilarious code. Wait. Where is it? Totally innocuous file. Okay. What the hell? What is this doing here? Jules! He's got a bird in sight. Are you meowing at the dog next door? There's a pit bull that lives next door that my cat is infatuated with. He's just like, here, you can look at him. It's kind of hard with all my cords and wires. I don't know how much visible he is. Just look at him. He just sits. He just sits in the window, longing after the neighbor pit bull, who loves the neighbor pit bull. They want to be buddies. Unfortunately, I don't let Jules outside because I like having birds in my neighborhood. Infinite recursion equals fractals. Yeah, fractals can have endings. Usually if you're doing a fractal image, then your base case is when you reach the pixel level of your image. Alright, so what's this code do? What does this code do? So it permutes. So you give it a string, and it will return all of the different orderings of that string. So let's, whoops, don't run that. We'll run this. Int object is not iterable. What? 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 Oh, what to append? What call do I make? So what call do I make for possibilities? So I'm gonna call it with remaining letters. And then what do I append? Why did I do this to myself? I didn't want to have to think. Oh, options dot word at character index plus possibilities new word index, and then we run it. Please work. What? Int object is not iterable. Oh, what should be returned? What should the base case be? If not word, we return an empty list. So if the word is an empty string, we'll just return an empty list. No! What is going on? There's people talking about infinite birds and being bourgeois. I'm not entirely sure. Oh crap. I think I've stumped myself. Curse you, past Ben. For character index in range. Okay, possibilities equals permute remaining letters. And for new word index. We add these things together. Why doesn't this work? I'm curious about how my life has come to this point. Do you use PyCharm? I sure do. What's happening here? How is this not working? I'm very confused by my own code. This is why. Word's rog. So we started with frog. Now we're at rog. Now we're at og. Oh. If len word. This equals 1. Return that. Maybe that's the problem. Just, okay. What this is doing is you give it a string and it prints out all the possible shufflings of the letters. So the base case is if there's one letter, there's only one possible shuffling. And then what we do is we make as many recursive calls as there are letters in the word to shuffle it around. So I pull out F and I say, give me all of the different orderings of ROG. And then after I do that, I put F in front of all of those. Then I pull out R and I say, give me all of the orderings of FOG, which is what's happening down here, and then I do that. And then I pull out O and then give me all the orderings of FRG, and so on and so forth. Here's the thing though, if I do frogs Look how many of these come out though. And this is something you'll learn in 203 is like how many of these can be produced. All right, there's a lot of different organizations of frogs. How about Frogs Rock? Is it gonna finish? There's a lot. My computer's fan just turned on. You don't want to leave something like this running because it just chugs. So yeah, it turns out if you make it the frogs and we hit the tipping point, right? Or just keep coding in putty like God. I do recommend eventually, maybe over the summer, getting familiar with PyCharm or CLion or some other integrated... Oh, look, it finished! Integrated development environment, IDE. They do help out a lot. That you can use the debugger more conveniently. It's just really easy. It makes your life so much faster. Yeah, is it cool when somebody can paint a masterpiece in MS Paint? But, like, would you expect them to do that, like, if they were a professional illustrator, to use MS Paint? So if you're going to be a professional programmer, using professional programming tools seems natural. It's not a crutch. It's a helpful thing to do. It is VI or bust. Bust. Nano. It comes on every distribution of Ubuntu by default. You don't have to install it. It has all of the necessary shortcuts you need to do basic file editing right there at the bottom in case you forget. Nano. Ease of use. Nano for life. Hashtag test as you go. Hashtag Nano for life. I actually used Emacs for a long time, but I prefer Nano. Because I don't do actual coding in the terminal. I might, like, adjust configuration files, but I don't do actual coding. All right, guys, that's 201 for the day. That's your second classes. Concludes our discussion of recursion. Next class, I think we're going to go into counting systems, and then next week will be the exam. It will be take-home. We haven't yet written it, so we don't know how long we're going to give you to do it. I guess it's Minecraft time? Is it Minecraft time? Is it Minecraft time? Or is it not Minecraft time? Uh-oh. Uh-oh. Is it Minecraft time? Charlie says it's Minecraft time. Minecraft time. So Patrick says he has a situation in Minecraft, a bunker of sorts. You'll have to come to the spawn and show me where your bunker is. Or if you're in your bunker, I can teleport to you. Bye, Kyle. Have a nice day. Invalid session. What? What? It's my server. Did you guys kick me out of my own server? Is the server down? Patrick can... You're in the bunker. Patrick's on the server. Oh, okay. So the server must be up. I mean, it says there's one person in it, so... It's letting people join, just not me. I restarted the game in the launcher, though. I just did that. I just did it. You seemed like you could use help. Oh man, Cam's in the game. Everybody can join but me. Except now. I died? I logged in and immediately died? Oh my gosh. Oh, someone blew a hole in my house. Where did I die? I lost all my crap. Alright, teleport. Me. Whoops. Teleport. Crazy Doc J to... Oh, okay, we're following him. We're following him to his bunker. This is a lot of colorful livestock. Wow, you guys have really tidied up the place. Wait, where did... Oh, there he is. I am just an unequipped hot dog. So this is... Okay, here we go. This. This is a long stairwell. I feel like something horrible is about to happen. This is quite the bunker. This is okay. It's very circular. Oh, it comes back up. Oh, interesting. Take what you need. So it. Oh, I see. I closed the door. So yeah, I guess he's got a little like circuitous path here. Oh, there's a monster. Patrick, there's a zomboid. Patrick, a zomboid, help me. Patrick, there's a zomboid. Patrick, I'm scared. Oh my god, Cam to the rescue. Oh my god. Oh, defend the hot dog. Oh. Are fish eggs fish? Oh, look how tastefully lit it is. Wow, who did the wow. Who did the plant? Who did the piranha plant? God, look, it's Mario. Wow. This is, wow. Clear weather, yeah, weather, clear. Is it, how do I set day? Set, is it time? Creeper. Uh-oh, Cam, there's a creeper about to get our precious. Oh my gosh. Is there anything else to look for, guys? Yeah, we've got Sean Joe's so many people. Yeah, we got a lot of people on here. Very well. Welcome to the Oats of Hell. Gates of Hell. I thought it was a reference to Professor Oates. Not exactly somebody that I would equate with hell. This seems ominous. You know, this seems ominous. Oh, it's another creeper! Patrick fills in the ground. Wow. This is just, I can't even. I absolutely can't even. Well, guys, that's today's tour of Minecraft. I don't know how the TAs are going to one-up themselves. That's damn impressive. Is this a Coliseum? Yeah, I don't know. Maybe we'll have some sort of TA battle royale in the Coliseum at the end of the semester. 7 TAs enter. 1 TA leaves. Alright, guys. I think that's going to wrap it up for today. You'll generally get answers. You can tag the TAs as well. Please don't annoy them, though. Like, don't do it at, like, 3 a.m. Try to keep your mentions to business hours. And we'll help out. Sometimes I see stuff at like 1 a.m. and I have to be good about not working 24/7. I know that's what you guys would probably enjoy. But all right. Yes, I've seen the scale version of Minecraft. It's pretty terrifying. Anyway, have a great Tuesday, and I'll see you guys on Thursday, and we'll talk about whatever the next topic is. I believe it's counting systems. Yeah, that's Curtis. Not to dox Curtis. Uh-oh, am I about to be blown up in Minecraft? Alright, guys. Have a good one.